Quick advertisement. It turns out I have no friends who tweet. I need to find tweeters. Tweet that hashtag build Baymax. And if you want to make the extra effort, you can go to this webpage and pick your favorite photo and tweet that too. This is the new RI funding model. This is how we're going to get Siwan through the rest of his career. So if you care about Siwan, care about graduate students, tweet away.
All right, and with that, we'll start. So we're very happy to have Wojciech Matusik here as an RI seminar speaker today. He's an associate professor at MIT. Before that, he was at Disney Research Zurich, where he did a lot of cool stuff related to fabrication and other things. And before that, he was at Mitsubishi Electric Research, I believe. Adobe. I missed Adobe.
Yes, sorry. I was traveling too much.
Yeah. So he's had a bunch of cool industrial careers and is now a professor at MIT. And he's going to tell us about multi-material 3D printing. Thank
you very much for the introduction. Thank you for you guys being here despite some of the looming deadlines in 30 minutes. Okay, so the topic here is multi-material 3D printing and especially abstractions for multi-material 3D printing. So if you go to any type of press, a popular press, there's lots of 3D printing over there. So this is various magazines, books appearing in copious amounts, and even in some of the business journals. The interesting question, I think, is what is 3D printing used for these days? And there's a very nice survey that's done by Wallers. And it shows roughly that about 50% of the usage of 3D printing these days is what we typically think of 3D printing, where it's basically for prototyping, for research, for presentation materials. And then there are these two parts that are very rapidly growing. So one of them is manufacturing. So this is uses for tooling and for making molds. So roughly quarter. And this green part, which is really rapidly growing, which is basically manufacturing of real functional parts. So parts that will be actually used in actual products. This green part was really not existent maybe 10 years ago, and so pretty much expanded from 3% to 25%. So this is very, very interesting to look at these trends. I would like to give you some examples of multi-material 3D printing. So for example, Aston Martin is doing some car prototypes. So they are basically manufacturing these almost life-size car models, and they are putting them, of course, together. And some of these cars have been used for James Bond movies as some special effects props. They, of course, were crashing probably then, and these cars would be probably too expensive to crash the real vehicles. GE Aviation is really trying to look into multi-material or in 3D printing in general, specifically in metal printing. So this is a fuel injection nozzle that's used for real aircraft, and they have shown that actually they can build metal parts that are more durable, that are lighter, and they combine within this part traditionally 18 different components that were sort of built separately and then put together. And they are actually making over 45,000 of these parts for various planes. Nike has been also looking into additive manufacturing. For example, they show these football cleats. They advertise these high-performance football cleats, and specifically the cleats of this football shoe they are 3D printed, and they are marketed as the highest performance football cleats on the market. So this is something that you can potentially buy these days. Hobbies, makers, and prosumers are also really embracing this trend. So this can be anything from scanning and 3D printing different figurines to making real functional little devices. For example, this tape measure has been designed and 3D printed using very low-cost devices. And similarly, this 3D printed caliper. So these are some of the parts that actually people can design and fabricate. I would like to actually focus a little bit more on multi-material fabrication, because this is what my group is really heavily investing in. So what is multi-material 3D printing? Well, I'm going to explain on a very simple example. If you are going to take a given model, let's say this piano, you can discretize it in little small building blocks, volume elements, and then we are going to essentially take each of these volume elements, and we have an option of assigning a given material from a given material palette, right? So for traditional printing, we can just say whether there is a material there or not. For multi-material 3D printing, we can basically put some type of material within each of these building blocks. There are at this point quite a few different multi-material 3D printers on the market. Both 3D Systems and Stratasys have materials that are currently available and printers that are available. So for example, this is the line of Stratasys printers. They can potentially print very large volumes. For example, almost life-size bicycle parts. But there are lots of downsides to the current state of the art. So the hardware, as you have seen, is expensive. The materials are quite expensive as well. The materials have the material library is fairly limited. These systems are very, very close. So you really cannot really change them, and you cannot really experiment with them. You can use only 2 or 3 materials at the same time. The software is fairly limited. There are very limited ways in which you can interact with the printer. There are, I think the software in general is in very, very poor shape. There are really no good material design tools. And in general, they are very, very hard to use. So I would like to discuss really briefly what is our approach in terms of hardware. So hardware, we have been building hardware for the last 2-3 years. And our main really focus was to use computer vision to assist in developing the hardware. And using some of the techniques that I'm going to show you, we can really build from relatively low cost, low quality components. We can build high resolution hardware with resolution up to 30 microns. All the hardware components are low cost. We can print with 10 materials simultaneously. Everything is is open, extensible, and you can really integrate things. You can integrate both the 3D printed parts with auxiliary non-printed components, and you can add additional print heads or different parts to this platform. So this is the hardware prototype version 1.0, maybe from a year and a half ago. It has standard XYZ positioning stage. It uses inkjet-based piezoelectric print heads, consumer off the shelf that are adapted to 3D printing. And so they are mounted here, and everything is fairly modular, so you can add additional components on this tray if you want to. This is the second version of the prototype, slightly smaller, that you can actually put on the desktop. But in general, the functionality is pretty much the same. We use computer vision to calibrate the system. So there is actually a camera over there on the board. So first of all, you can use the camera to calibrate your system, to calibrate your positioning system to the build platform. So that's first step. And you can use you can also print with various nozzles on this printer, and then you have either user-assisted or automated system to actually detect where you print, and you can basically calibrate everything. You can calibrate your printing positions to the printing system. Another interesting feature of this system is that we actually have a complete 3D scanner within this loop. It's an interferometry-based scanner that allows you to scan at very, very high resolution. And this enables, of course, quite a lot of different applications. So I think what you were seeing here are the interference patterns that are forming as you move the platform up and down. And from that, you can reconstruct the depth fairly accurately. What this is used for is actually corrective printing. So in corrective printing, you are going to start printing with your desired model, and this model in particular this layer is supposed to be flat. In this case, you are going to see that this layer is actually not flat. As you scan it, you send a correction layer, and then after printing this correction layer, everything sort of is within the limits of your printing resolution. You can also 3D scan auxiliary parts on the platform. So you can, for example, scan 3D objects that you place on the platform. What this is nice for is that you can actually print 3D objects directly onto auxiliary objects. So for that, you actually need another component, and this component is alignment, right? So we actually have an interactive alignment system where you can take a given 3D model or 2D image, and you can interactively align it with the model that you would like to print. So this is very nice functionality because many objects you actually cannot print. So this will provide you with a way of embedding non-printed parts within printed components. I would like to show a few examples of what we can do these days. So for example, here we can print Microlens arrays. We can print them directly on the screen. So for example, if you'd like to print a Microlens arrays directly on a screen, you actually could do that fairly easily, and you can align the microlenses directly with your screens. And here, this is a multi-material print where these baffles here around each of the lenslet are actually printed with a different diffuse material. You can start printing different metamaterials. For example, you can print structures that have both empty space and rigid and elastic materials. And you can build structures that, for example, have negative Poisson ratios such that when you expand them, when you are going to stretch them, this direction is going to expand. We can print textured objects. So at this point, we can pretty much almost print full color prints. We can print things like fabrics, so very thin sheets with embedded colors or other types of properties. We can, of course, print functionally graded materials, so where basically you can start with something that's very flexible and go to something that's very, very rigid. So in general, you can start mixing up to 10 different materials within this space, and we are really exploring, and we are adding more and more materials to the material library. So this really summarizes what we can do right now with the hardware, and I would like to sort of move on to the software part. I think this is quite interesting. So software. Multi-material printers exist right now, and you can print with them, but when you actually go and look at the current industrial use, you will see that people typically will print parts by assigning only one material to a given CAD model. So there is really no spatial variation in materials throughout this part. So the question here is, why do we do that? Or why do people do that? And the first reason comes from traditional constraints of manufacturing. So the current designers still think in terms of designing parts with only one material. So we really have to start thinking about how we can actually design parts taking materials into account with having this very fine grain of control over materials. So that's one thing. And then the second is really that we really do not have proper design tools at this point. So standard modeling packages, for example, CAD packages like SolidWorks or AutoCAD really do not provide that kind of functionality. And finally, we really do not have scalable software architectures that would take care of these constraints. I'm going to talk about two different ways in which we can aid some of these problems, and I'm going to talk about how we can improve the specifications for 3D printing. And when you talk about specifications, it's really important to observe there are really fundamentally two different ways in which you can specify materials. Each of them is really, really useful. So if in one way, which we call direct specification, if I would like to build a piano, this piano, I'm going to say the top of the piano is made of particular wood. The strings are made of, let's say, copper, and these keys are made from some particular plastic. So these are direct specifications. In functional specifications, I'm going to specify the function of the object rather than materials directly. So for example, I'm going to say that the top of the piano has some particular gloss level, and if I, for example, hit, I'm going to apply certain kind of force to these keys, I'm going to obtain given sound from this piano. So this is specifying objects more in terms of their function rather than specifying materials that go into these objects. So let me talk first about direct specifications, the challenges and the solutions that we provide. So in direct specifications, there are the following 4 main challenges. The first challenge is that when we print at this very high resolution, let's say we print at 600 dots per inch. If we print a cube of material, we have a gigavoxel of data. If we print a cubic foot of material, we actually have teravoxel of data. So this is fundamentally, we have lots of problems with the data size of the whole model. It's really difficult. The second challenge is that specifying continuous gradation between 2 different materials is inherently very, very hard using current modeling tools. So for example, if you would like to have some structure that goes from one material to another, it's very, very hard to do it at this point. We also do not have proper reusable material definitions. So if you would like to define some material structures, we can really reuse it later on. And the current tools really do not provide printer and resolution independence. So everything is set for a given printer. We would like to have tools that really abstract that. So our solution for this task is OpenFab, and OpenFab is the first programmable and scalable fabrication pipeline for direct specifications. OpenFab is inspired by rendering pipelines, specifically by Pixar's RenderMan and by current GPU architectures. Similarly to those, it has both fixed stages and programmable stages, and it allows you to do procedural surface definitions and material definitions, and provides, as I said, resolution independence. And in order to implement this, we show that we use a streaming architecture to make sure that we can handle the large data sizes. Let me talk briefly about the programming model. So this is similar again to GPU programming model or to RenderMan, where basically we have input, we have fixed function stages, where basically we tessellate, voxelize, and dither, and we have the programmable stages, in this case 2 different programmable stages, which can take care of, which can use some of the textures and materials, and we generate the output. So let me walk you through the whole pipeline. So we start with an input, and in our case, the input are shapes, also boundary representations, for example, standard meshes. And when we also provide fablets. Fablets are little programs that allow you to specify the surface detail, and they also allow you to specify the volumetric material composition. We also specify resources in terms of textures and materials that we are going to use. So in the first step, we tessellate the object. So we're going to take this surface representation, and we are going to tessellate to a small micropolygons at the size of our printer resolution. And then we have the first entry point to our programmable stage. So in this stage, we allow the surface to be displaced. So there will be a little procedure that's going to displace the surface. So for example, if you would like to have a surface that has certain friction, or to add some friction to that surface, you would create some procedural model that would add that kind of microstructure for that. If you would like to have an appearance of some crocodile skin on this teddy bear, right, you would probably read it from some small texture patch and apply it across the surface. If you would like to distort with this, in this case, with some Perlin noise, like Perlin noise displacement, you would actually obtain something like that. So that's the surface stage. The next stage is the voxelization stage. So we are going to take this displayed surface and we are going to voxelize it at a very, very small resolution, at the resolution of our printer. And then I think we enter the most interesting stage in the Fablet. This is the volumetric stage of the Fablet. So we are going to execute the stage for each point in the material volume. So for each voxel, we are going to call this procedure the volume Fablet. And this procedure is going to take as input x, y, z coordinates, and it's going to return to us the material composition at a given voxel. So in this case, we are going to say for this particular volume element, I would like the volume element to be 50% material A, 25% material B, and 25% C. And then we enter the last stage of the pipeline, which is the dithering stage. So in this case, most of the current printers really cannot handle continuous material composition. They have to put some particular material at a given voxel. So in order to handle our abstraction, we have to take this continuous input and distribute this input locally. So this is very similar to the way we do 2D printing, right? Where we specify the colors RGB at some resolution, and then when we actually print them, we have to sort of assign some given colors. And so in this case, for this particular voxel, we are going to assign some material A, and then in the neighborhood, we are going to assign specific materials such that the overall error in that neighborhood is distributed. So in this case, we would use something like Floyd-Steinberg error diffusion algorithm. And finally, we have the output. I would like to talk a little bit about OpenFL and Fablet. So OpenFL is our domain-specific language that allows us to specify these little procedures both for the surface stage and the volume stage. So as I said, a Fablet is specified, one Fablet is specified for each object. It has 2 entry points for the surface stage and for the volume stage. And I just would like to briefly show you how these little programs look like. So this is the surface stage of the Fablet. It returns no displacement in this case. This is the volume stage of the Fablet. It takes the voxel center. And one particular interesting application here is that a very common application is that you would like to, for example, design some composite material, multi-layer material. And in this case, I would like to have an object that within some 1 unit distance from the surface, it's going to return some red material. Between 1 and 2, it's going to return blue material, and otherwise a yellow material. So to take advantage of this, we are going to use this signed distance function, which basically evaluates signed distance from the surface. And then it becomes a very simple if statement to determine which type of material to use. I would like to briefly mention how we construct the architecture. So a big part of this is actually to actually build a reference architecture that runs and sort of outputs all of these models. We really have 3 different objectives here. So first, we would like to have a very fast startup time. So whenever we issue a print, we would like to we would like the printer not to compute the whole model, but we would like this printer to start computing and printing data. We are going to use slab-based data structures. So in this case, we are going to allocate some slabs within the memory, and we are going to that can store up to some number of slices, and we are going to print them in the vertical, of course, in the vertical direction, and from the bottom to the top of the model. And of course, everything is going to be streaming, so these slabs are going to be continuously streaming one by one to the printer. This is how the architecture looks like. Most of this part is really pre-computation of the acceleration structures to make sure that things like the sign distance functions can be actually accelerated, can be run very, very fast. And then this is the main loop that executes the pipeline for each object and for each slab. So and after each slab, it's going to output it and send it to the printer. The interesting part about this pipeline is, of course, what can we do with this? So first thing that we can do is material decoupling. So what does this mean? Well, it means that we can have one input geometry, but we can specify different types of surface and volume fablets for this geometry. So in this case, we have one Rhino, 3 different fablets that specify how the materials are distributed throughout this object. What is also very interesting is that we can reuse materials. So in this case, I can define some specific operator that's going to define this foam-like structure, and this is going to be one particular fablet. We can apply this operator to this teddy bear, and we can reapply the operator to let's say the Stanford bunny. So of course we can build a whole large library of these operators. This example shows the power of the procedural surface definitions. In this case, we can specify these lenslet arrays analytically. So the shape of each of these lenslets are specified analytically, the baffles and the baffles as well. And then the surface stage of the fablet is going to distort the surface here. So the input is just a slab of material, and then the surface fablet is going to distort the surface appropriately to make sure that we are printing each of these lenslets at the resolution of the printer. We can also do procedural volumes. Procedural volumes allow you to essentially to define, in this case, materials, marble-like materials or any type of material throughout the whole volume. In this case, we use Perlin noise-like procedure to define this marble-like behavior. And of course, it allows you to do something even more sophisticated. You can, this framework allows you very easily to define structures like this, where you have changes of index of refraction throughout the whole object. In this case, you can, this particular structure allows you to change the direction of the light from one plane here to arbitrary surface on the other side of this optical fiber bundle. And of course, you can do it in 3D as well. You can, in this case, you just couple the surface to a monitor and then and compute these fiber directions that relay the light to the other part of the surface. So this is something that's fairly easy to do with all of these phablet operators. It also allows you to do designing and building more functional parts. So in this case, we have designed this ping pong paddle as SolidWorks as a shell, and the whole material composition, all of these little displacements are all coming. So these displacements are coming from the surface fablets. These little dimples on the front side here. All of these foam-like materials are also built in using fablets, and again, these types of nice appearance look is also built using our fablets. So in general, you can start building more and more appearance behaviors, more and more complex mechanical behaviors, and reuse a lot of the underlying data structures and code. This is another example. This is a ski. The bindings are not printed, but this is something that could be a pretty good functional prototype of a ski, where you can both prototype the very nice appearance here of the ski and mechanical properties of the whole structure. So this really shows you the power of these techniques and what kind of things you can actually do with them. When we talk to designers, in many cases, designers really don't like to work with direct specification. In many cases, really, they don't really care what kind of materials they would like to use. They more care about the functional properties of materials. So in this case, it really brings us back to these functional specifications. So how do these work, and how can we really design frameworks around these? So, as you can imagine, there might be many different instances of and many different kinds of these functional specifications, and we in this particular, for example, this particular kind of some functional specification, we are going to develop a special process that takes these functional specifications and translates it to the printable object. So how would this type of framework work? So let me go through something that's very, very naive. So let's say I would like a piano that is going to play a given sound. How can we build this kind of piano? So at a very high level, I can assign some materials. I can try some assignment of materials to different parts of the piano. I can have some physics-based simulation, and I can simulate the sound here, and then I can compare the results of the simulation to the goal. If this goal, if this comparison turns out to be good, well, then I can sort of say I'm done. I can print. In this case, this is not the case, right? So I can try another material combination. I can simulate things again. I can compare to the goal. In this case, it matches better, so I can say, okay, this is good enough. I would like to print. Well, the problem that this type of approach doesn't really quite work when you work with 3D printing. And the main thing is that the whole possible design space is way too large. So even if you were to take a 2-inch cube of cubic inch of 2 cubic inches of at 300 dpi and 3 materials, you would have a really large number of different material combinations to try. So this really quite doesn't work. So we have to really work with some different types, with some solutions really that solve this problem. Okay, so this is this naive spec to fab translation process. How do people try to solve these types of problems? I think the most interesting way of solving this problem is do not work in the original space of all different material combinations, but work in a reduced parameter space. So we are going to take all of these parameters that describe variables for each of the voxels, and now we are going to work with a much smaller set of parameters that are constructed in some particular way. And using this reduced parameter space that's potentially lower dimensional, we can perform this simulation and optimization processes in order to achieve some nice desired material properties. What's really interesting is that we have looked at many types of instances of these processes in computer graphics, and we saw that really people have tried to tackle these problems both in computer graphics, in material science, in robotics, and all of these processes really share this very similar structure. What's really even more interesting is that a lot of the building blocks are very similar. So for many of the, for example, for simulation, for these comparisons, for optimizations, people came up with a number of building blocks that they keep reusing all of the time. What's really, I think, what's the most important and what's the most important and what's most interesting in the space are the reduced parameters. Can we build a small set of common components for these reduced parameters to construct the space of these reduced parameters? So in order to actually deal with this, we have came up with 2 different data structures. Right? The first data structure is reducer tree. The reducer tree data structure allows you to parameterize the space of the solutions. And then the tuner network encapsulates the whole optimization and simulation process. Okay, so what is a reducer tree? So a reducer tree is fabrication-specific hierarchical decomposition of the whole space, geometric space of the object. And it's going to give us a non-overlapping division of the whole object. So how does this work? We are going to have some internal nodes within this tree. These internal nodes provide spatial partition. And we have some leaf nodes. And these leaf nodes mostly provide material assignment. So we analyzed a number of different algorithms, and we sort of looked what are the typical types of partition nodes that people use. The interesting part, one of the more interesting ones is the stratum node. The stratum node is going to take arbitrary geometry and some parameter that takes some shell thickness, and it's going to return two pieces of geometry, the external shell and the internal core. Column subdivision is going to take geometry and subdivide it into columns. Voxel data structure is going to subdivide the geometry according to some voxel grid. Plane data structure is just going to cut the geometry with a plane, and some spline subdivision is going to separate the geometry using some spline. The leaf nodes can provide material assignments. So these are, let's say, these are different assignments that your printer can print. One of these materials can be also void. We can also have parameterized material structures. So for example, we could have some foam-like structures that have low number of parameters, and so in this case, the parameter that I have here is just the radii of these foam bubbles inside of the material. Or in the case of a layered material, I would have just the number of layers and the materials assigned to these layers. So how does this work? Well, we have taken, for example, one of the algorithms that we have designed, and we have tried to construct a reducer tree for this particular algorithm. So first, in this case, we are going to take an input shape, and we are going to subdivide using the stratum node. Then we are going to take the external shell, and we are going to subdivide it using the column partition. And then we are going to assign just one material to the stratum node in this case, because for this particular application, the internal material within this node really doesn't play that much of a role. And for each of the columns, we are going to assign these layered material structures. So fairly simple reducer tree, but already provides you it provides you a pretty big reduction in terms of the parameters that you're actually going to use in this optimization. So what are the parameters? The parameters are, in this case, the thickness of the stratum, the number, the width and height of each column, right? And then in this case, the material IDs that you assign to particular parts, both for the internal material and for each of the nodes on the bottom. Okay, so now we have our parameterization space, and for a given assignment of materials and values of these parameters, we can potentially start evaluating the fitness of our solution. And in order to do this, we have to start using tuners. So tuners are basically these abstract data structures that encompass both optimization and simulation. In this case, I can take tuners and I can connect it to any of these nodes in these data structures. So when I connect the given tuner to a given material node or given node in this tree, it's going to be responsible for optimizing all of the materials within the subtrees that's inherent to this node. So for leaves, it's just responsible for optimizing the material for the leaf node. If I connect it to some internal node, it's going to be responsible for optimizing the materials within the whole subtree. So how does this work? The tuner is going to collect the tunable parameters. It's going to run its optimization and simulation, and it's going to tune these parameters and update the parameters after it's done. We can, in general, we are not going to have just separate tuners, but we are not just going to have a single tuner, but we are going to have the whole tuner network, so we can attach these tuners to different parts of this tree and schedule how they should optimize the whole data structure. And we also allow these tuners to communicate among each other. So in this case, these tuners can share some information to propagate information faster. I would like to show some results. I'm going to start with something very simple, something very basic. So this is a spec to fab for texture. This is something very, very basic, right? So our goal in this case is a given texture. We are inputting a given geometry and a texture, and we would like to obtain a material, a print that has this given appearance and geometry. So the tuner network and the reducer tree looks like this, so it's fairly simple. The nice thing about this is that once we define these data structures, we can pretty much apply it to any other geometry, any other texture, and sort of still everything works in the same way. As you can see, we can also reuse part of this work if we would like to, for example, optimize things for given translucency. In this case, the reducer tree stays pretty much the same. What's changed are just the tuners. The simulation package, the simulation that we are going to use is going to be different. And of course, once you have this, you can apply this to arbitrary geometry as well. This framework also allows us to compare different algorithms that achieve pretty much the same thing. So during the last couple of 3 years, we have seen a number of algorithms that achieve pretty much the same functional goals. In this case, caustic images. So in this case, what happens is that you have a light source that you shine through this little lens, and you have a special custom lens such that this lens is deforming how the light is sort of propagating and causes this essentially and causes these nice images appear at some given distance. So the goal here is just the image, and the output is the shape of this lens. So for some particular algorithm, we have this given reducer tree and tuner network. For another algorithm, we can observe that both the tuner and the reducer network has completely changed. So it's very nice to look at these algorithms and see what's different between those. What's also nice about this framework is that it allows you to combine many objectives together. So we can potentially start building things that have a couple different properties that work together. In this case, we would like to have certain mechanical properties and certain appearance characteristics. So in this case, we are going to design this type of tuner and reducer tree. So using this kind of framework, you can potentially start building many interesting algorithms. You can combine many things, and I think this is something that people really, really want, especially in the design community. So how do these pieces work together? At the bottom here, of course, you have hardware, right? And direct specification layer is going to communicate directly with that hardware. And then functional specification is going to communicate to the direct specification. So the output of functional specification is going to be the input to the direct specification. Is this all? Of course not, right? You would like to be able to build applications and interactive design tools on the top of this whole stack. And these applications should communicate both with the direct specification and with functional specification. So for example, certain parts of the objects, maybe for certain parts of the objects, I know what kind of materials I would like to use. So I'm going to use direct specifications. For certain parts, I would like to use the material properties. I would like to optimize the shape. So I would like to have access to actually specify the properties of these structures more functionally. I would like to show you a few examples of the applications that we have built on the top of these frameworks. So the first one is a multi-material design studio. This is an equivalent of the multi-material CAD. You are essentially starting with an input shell of the objects. You are loading this, and you are going to start building a network of different operators. This is very similar to shade tree-like operators, where you can connect many different things together and build progressively finer and more complex structures. So in this case, we are building a tire that's a combination both of a tire and the wheel. And as you can see, the user in this case builds progressively fine and final structure. This is still very, very compact representation, but something that results in a very, very big model that probably has teravoxel of data. Underlying representation is probably less than 1 kilobyte. Right? So this is very, very powerful because it allows you to build something very, very complex with complex mechanical structures from a set of relatively small number of operators. We have implemented implemented maybe 100 different operators that provide different types of features. For example, different types of substructures, different types of subdivisions of the volume, different types of parameterization of the whole space. So in using this, you can build things like this. We of course are not tire designers, so this is just an example of what you can do with this type of framework. Another example that I would like to show is computational design of mechanical characters. And so this is a very interesting direction because it allows you to potentially do something that other people could do, but it was very, very hard. So this is how the system looks like, where the input is just a rigged character. So it's an articulated character. And in this case, the user is just going to specify a given joint or a given point on this character, and is going to draw interactively a given motion curve. And the system that we have been building provides the underlying mechanism that's going to provide this given functionality. And once you specify all of these motions for most of for all of these parts for all the legs, in this case, you can actually obtain and print characters with very complex motions. What's the insight here? Well, I would like to say there's really no free lunch. The system cannot really figure out how to do it by itself. You have to sort of start with something. So our intermediate representation here is this library of mechanisms. So we are going to take different classical mechanisms and we are going to parameterize each of these mechanisms. So in this case, if this is a 5-bar linkage, we can start picking different parameters of this 5-bar linkage, and as you can see, as we change them, they result in a very, very large collection of different motion curves that are spanned here. So as you can see, lots of different motion curves with this very simple mechanism. The next part here is that in general, the space of all of these motions is fairly large. So in order to actually guide the search process, we would like to actually we would like to store this sparse database of representative motions. And then when the user is actually drawing these motion curves, the underlying system is going to retrieve the closest mechanism, use it as a starting point for an optimization that's going to actually to synthesize something that's very, very close. But this can be, of course, this optimization is going to be very, very fast because the underlying curve is already very, very close to the underlying input curve. There are a few bells and whistles in the system. For example, if you would like to have phase offset between different legs, there's a fairly simple way of joining different mechanisms together to guarantee that. If you would like to have different velocity profiles, this can be accomplished with non-circular gears. And once you actually have defined the motions for all of these mechanisms, and you have all of these mechanisms defined, you would like to typically drive it with one motor. And there is a fairly simple user interface that allows you to add the number of required gears, and the system automatically joins them together. So these are some of the results that we have designed. Some of them have been fabricated, and I'm going to show a few of those. So this is something that would be fairly difficult to design by casual user, and in this case, this can be done in a matter of a couple hours, and fabricated using multi-material printer. The driving or the gearbox doesn't have to be external to the mechanism. It can reside within a given mechanism. So this is fairly simple. You just constrain where you would like the mechanism to be placed. And this example shows that we can combine motions in different planes to obtain 3D motion. So in this case, you can observe that you can actually have a complex motion for the tail of this T-Rex. There are obvious limitations here. These are still automata. These are still kinematic mechanisms. So obviously they fail and they are not real robots. I think the interesting future directions here is actually to make these guys really work. So I would like to move on briefly and tell you about the last application. How to design even more complex things, right? So how can we take this notion of this mechanism and how can we go further? How can we build more and more complex things? For example, how can we build or 3D print cars or maybe rockets to Mars, right? This is actually potentially very interesting. So obvious observation here is that when you take standard graphics models, right, the standard graphics models that you have are not really, they do not really represent many parts that are in traditional CAD designs. So for example, all of these things will be completely absent from these designs. So how can we approach this? So the approach here that we have been taking is to actually employ the users or mechanical engineers to capture the knowledge that all the mechanical or electrical engineers have into the database of designs. So we have been building databases of shapes. So we have worked with more than 10 mechanical engineers that have been designing many different CAD designs that span a few different categories. And immediately when you look at fairly simple design, you will see that it has hundreds of thousands of different parts. What we actually made sure is that each of these designs is manufacturable. So all of our designs actually correspond to real things, something that you can actually go to a given catalog, order, and buy. What is also interesting here is that we have made all of our designs parameterized. Building or designing each of those designs is very, very hard. So in order to span a much larger design space, we actually make all of these designs parameterized. So these parameters can be both continuous or can be discrete. So for example, as I change the sizes here of these shelves, the underlying number of connectors is changing as well. So this brings us to our modeling tool, and I would pretty much say this is more of a composition tool. How does this tool work? Well, you can of course start with any given design, and you can change its parameters. So this is a simpler way of navigating the space, right? And it already gives you quite a lot of freedom in terms of what you can do. What is really actually fun is taking different parts of different designs and actually fusing them together. And for this, we actually provide a few different interesting tools. So one of these tools is actually snapping components together. So once you start bringing two components together, the system is actually figuring out how these guys should be connected and how the constraints should be applied. We can also handle some articulated models. For example, if I would like to have this shelf and I'm bringing the doors, the system automatically knows that the sizes of these doors should not overlap when you close the door. We also bring connectors and support structures. So we look into database, into corresponding designs, and when we bring two pieces together, we are going to figure out what are the connecting pieces to actually that make it into a functional part. And this is an example that shows that if you are going to pick two different, if you are going to connect two different things together. So in this case, if you connect two different, if you are going to connect this base to wood, and you are going to have completely different set of connectors. If you are going to have If you are going to have a glass tabletop, the connectors are going to be completely different. We think that physics simulation is going to be very integral part of this design space. We haven't really done a lot in this space, but this is a very simple check whether, and it tells us whether something is stable or not. So, for example, in this case, if we design something that's not stable, right, the system is going to be automatically highlighting that this is not a valid design. And this shows you a sample interactive modeling session where basically we just built a desk with a little bookshelf, and this is sped up maybe by a factor of 5 or so. So this is something that casual users can potentially use to design and build things. So at the end, of course, you have a bill of materials. You can get all of the parts, and you can manufacture this. What's really nice about this approach is that it really starts, we can apply it to other things. So if we have a different type of database, in this case a go-kart database, and its parts, we can actually build go-karts as well. Right? So the nice part about this approach is that if you would like to build maybe robots, and this is a very interesting future work, is we could potentially start building these robots from these components and have a very similar system for that. Okay. So this brings me to the conclusion of the talk. I don't think I have to convince you that abstraction is really crucial for fabrication, and there are really lots of interesting interactions even within from computer graphics to compilers to optimization to machine learning to human-computer interface. So all of this fabrication space really spans. It's not just graphics. It really spans much more. I really think that with the advent of these new output devices, I think it brings us closer to sort of democratization of the whole design space. So basically, users will be able to build anything they want in a simple way. I think that that computer science really is going to act as a glue here in this space, and we will see many more interactions between other disciplines. So, for example, we are going to see connections to material science, to mechanical engineering, to biological engineering, and architecture, and many others. But I think it's going to be really fun, and I think it's going to be very, very broad, multidisciplinary research. I would like to acknowledge some of my collaborators on the work. Without them, of course, none of this would be possible. And with that, I would like to thank you, and I would like to take some questions. Yes.
So I'd like to challenge I think the central assumption of what you're doing, which is 3D printing, or let's say manufacturing, is somehow like printing on a laser printer. And it would be nice if that was true, but I just don't think it is true. The thing about a laser printer is the resolution is so high that you bottom out at voxels or pixels in that case.
Yes.
It doesn't matter. The resolution of current and sort of foreseeable 3D printing technology is not high enough that you can ignore the quantization of voxels. And I think in making things, and more importantly, describing how things work, we should have bottomed out, I believe they're called stroke-based primitives, essentially the splines, and not go all the way to the voxels. And the other thing that's missing is something we do in manufacturing, which is a process-based description. So if I hand somebody a plan to make something out of aluminum, typically there's some kind of notation about how to finish it.
Yes.
And that's a description of a process. What they're supposed to do with a machine is not a description of a part. So I guess to really make concrete what I'm objecting to, I'm saying we've lost processes.
Okay. So
and one of the things we've lost is description of very small parts. If I want to make a load cell,
Yes.
there's going to be this little narrow neck I'm going to put a strain gauge in. I can't afford to have that sort of screwed up by quantization error and the sort of whatever
Yes.
of how your grid is arranged.
So absolutely, but I think this is the exact. This is the no. So I think the key is the abstraction, right? So abstraction is key to what you will like to see, and of course you can have many abstractions, right? And depending on what kind of applications you are pursuing. So to give you an example, I'm going to give you a very concrete example here. So in our case, we have said that our abstraction is having for multi-material 3D printing, we have voxels that have continuous compositions of materials inside. So that's our abstraction. Well, this abstraction, of course, works for some things. It doesn't work for some applications. For example, if the whole process of printing, right, in this case, multi-material printing, also depends on how you cure the material, right? So not how you deposit a given voxel, but also, for example, what you apply later to this. So this is, for example, not captured in this abstraction at all, right? We just completely ignore it. In order to extend this notion of abstraction, you'd probably have you would have something probably even more complicated, where for each voxel you specify a whole process that's sort of happening in order to make it into a given solid object. Or if you are working with larger primitives, right, you can specify it also as a process. But it's all boils down to an abstraction. An abstraction, and both the abstraction and the representation can be also a description of the process at some small scale.
Yeah, I guess I'm reacting to your picture that is essentially a graphics pipeline.
Yes.
Which I do think is tied to pixels or voxels. And
yes. But they do not have to be voxels. At some point, instead of being voxels, it can be this also can be little local descriptions of what happens at small scale.
Right. The thing about cooking, which
yes.
you mentioned, is it's a global process.
Right.
You can't independently cook each pixel.
Right. So
okay?
absolutely.
Finishing
and
is the same category.
absolutely. So I agree. And I think depending on the type of process that you do, you have to define your abstraction. And we have defined abstraction for one particular classes of fabrication devices. If you are working with some other manufacturing methods, I think you have to define your abstraction. And I think this is the whole. I think this is fun in this whole space, because each of these processes is probably going to have a different abstraction. And I think that's why I don't think you can use the same CAD tools for everything. I don't think it works. You have to design probably your abstractions and the underlying software and the computer-aided design tools for each of those. So if you are going to work with cells, you are going to use a different CAD software. If you are working with woodworking, you are going to use a different CAD software, and so on. So, yes.
But that in some ways is a permission of failure, right? Because like if you think, if as a systems person, you want to build abstractions that are general. And the minute you start saying that, oh, you can have a different one here, a different one there, you are now throwing up the white flag and saying that my abstractions are not good enough, I've moved up the stack, essentially. So the reason why OpenGL is so successful is nobody tried to include any of this other stuff.
Right.
They got the low level right and said, we'll throw up our hands on these other things.
Yes, so
the question, I think, is how is this going to emerge here?
So we have targeted specifically multi-material 3D printing, and we thought this is the right level of abstraction that we would like to provide. And I think it spans a sufficiently large class of things that you can do with this. Of course, it doesn't work for woodworking, right? It works for one particular process. I think it encapsulates most of the fabrication methods. So,
It would be interesting
of these kind of raster-based fabrication methods.
The question that one often asks about abstractions is what do you get from them? And I think that's a question that's going to take a while to emerge.
Yes.
Is it more than just syntactic sugar, or do you get something more, than just having to write a bunch of
I think abstractions are very important for the designers, especially in this case, because these designers are not going to work on at very low scale. The designers have to work at a much higher scale. Imagine basically building some complex part that has both electrical, thermal, and sort of mechanical properties. You have to provide something that sort of that hides the under.
In your sense, it's this notion of this optimizing simulation.
That is one abstraction.
That is the value add of what you're trying to do.
That's one way of abstracting this. So that's more higher level, but there's also some intermediate levels over there as well. So, yes.
So more towards the end of the talk, when you're talking about building functional structures. So like if I wanted to build, let's say, one of the chairs in this room, and like forgetting about the wheels to make it simpler, it was just a rigid body. Then, but let's say my 3D printer isn't large enough to, build the entire chair as one piece.
Right.
So then can I design the whole thing as one rigid piece and then have your program figure out how can I break this up into smaller rigid links, and then what kinds of screws, fasteners I need to put it together?
So, so that will be potentially, so in this particular work, this was not 3D printed, right? So, so the last part of the work was we were just working with traditional manufacturing, so there was no notion of so everything was had a given part. In general, you could of course you could of course decompose things even bigger blocks into something that can be potentially printed and fused together. So that's
something that's already available.
Yes.
But can the program figure out for you like where the most optimal places are to put the fuses, the places where you're going to fuse one piece?
How to optimally cut these objects? So obviously, yes, you can do these kind of things. We have even done some work in this space. This in general, this is going to be some multi-objective optimization as well, because you have many things that you would like to consider in this case. How many pieces you would like to have, what would be the strength of each piece, and so on.
Yeah.
So
I guess even if you weren't completely optimizing it, just doing something simple that's already available in SolidWorks, like you can just
don't count on SolidWorks. SolidWorks
so
has.
That's why I'm wondering, like, if that's something.
There are basically, I would say that many of these tools are completely not available at this point. This is.
So even something simple like that, taking a rigid large body and breaking it up into rigid links or fasteners.
So I'm saying that a lot of these tools are at this point not commercially available. There are lots of research prototypes that people have done. So I think the industry has to catch up with those.
I'd like to ask the audience a question. Does anybody who knows anything about circuit simulation like SPICE, is a description in SPICE a description of how a circuit works, or is it a description of how to make the circuit? Or is it good enough to make the circuit? Is there a fundamental distinction between those two things? Because, part of our questions have to do with this split between the functional description and how you make it description.
Well, the programming language people would just say this is the difference between declarative and imperative. That's what they would call it.
Yes.
Right, but I'm sitting here because I'm going to have dinner with a speaker, so I was thinking, okay, what are we going to talk about at dinner? Obviously, we're going to talk about rapid prototyping of food. What is the simplest possible description of a meal? Answer, get a hunk of meat and cook it, not where are all the atoms and molecules.
Mm-hmm.
So there, it seems fundamental that a process description, you can have all the functional descriptions you want, or it tastes good, or it's
You
perfect.
can take the other aspect of it and say, my description is I want something to taste good.
Yeah.
And have some simulator come up with the process that meets that design requirement. I might not always be happy with the process.
So if you're designing with discrete components, right? Radio Shack, 1980s,
Right.
5-pack resistors.
Right. Even today, do a surface mount board.
Yeah, so you can describe things in the functional level of this resistor connected to that transistor.
Right,
But if you're
right.
designing a chip where you're really concerned about, I want polysilicon here and I want a metal layer here, right? That kind of circuit you are looking at manufacturability, right? Because just saying that a wire isn't enough. You have to say what the wire is made of and where it goes and how thick it is. Right? So you have the choice of working at one level of abstraction or the other. Right? So you could imagine the same kind of thing in this space, where for some kinds of things, maybe you just say, figure out how to divide this up in pieces, and I don't care how you do it, and it'll do something reasonable. And for the other kinds of things, maybe you really care about which way the grain of the wood is running.
Right.
I mean, it's really interesting that we can draw a lot of analogies with the IC industry. Basically, we are around 30 years behind them, so it's kind of good to look at all of the stuff that these guys have been doing for the last 30 years and see how they have approached this, because there are many issues that are very, very similar. So I think they can be really a source of inspiration for a lot of work in 3D printing.
All right, let's thank the speaker again.
Okay.
And for those who want food, there's the post-seminar reception today.